Convair space manufacturing contract with the George C. Marshall Space Flight Center of the National Aeronautics and Space Administration. On many subjects, simple experiments can provide directly applicable answers, even though the data be only approximate. Here, significant characteristics of the liquid state are demonstrated at room temperature and under normal gravity, zero gravity being simulated for some of the effects by the use of the equal density tank. To illustrate liquid spreading, we applied droplets of water, ethyl alcohol, and naphtha to the top of rather thick glass plates so that the profile of the droplets shows as a shadow on the paper underneath the glass. Here we see the water being applied, and we note that the drop outline is rather irregular and that the shadow is broad and dark because of the prism effect of the water sitting at a high contact angle relative to the glass. This high angle ties in with the restriction of the spreading as indicated by the irregular profile. The alcohol forms a more nicely rounded drop. Its surface tension, and therefore the contact angle it makes with the glass, are lower, as shown by the less marked profile shadow, and it spreads more readily, continuing to do so after the supply is shut off. The little irregularities of the profile are where we see the shadow through the edges of the drop. The naphtha spreads quite actively. The contact angle appears to be zero, as it should. This is evidenced by the faint, rather diffuse shadow formed by the concavity where the very thin spreading layer is being followed by the liquid puddle. Some traces are just visible of the irregular profile formed by the evaporation of the spreading film. In the next sequence, we see two puddles of alcohol breaking into each other in order to illustrate that, for example, in adhesion casting or blow molding, two films moving toward each other can readily form one film with no discontinuity where they come together. A rather different phenomenon appears when a puddle of water is approached by some alcohol. The volatile alcohol evaporates and condenses into the water, reducing its surface tension, so that the high surface tension on the other side of the water pulls it away from the alcohol. The point is that the differences in surface tension can produce appreciable mass motion of the liquid bulk. Our next sequence shows a three-dimensional effect of a localized reduction in surface tension. Here we see a globe of water a little more than an inch in diameter, neutrally buoyant in a mixture of Freon 113 and naphtha, and above the globe a droplet of detergent which will reduce the surface tension of the water when it mixes with it. This is shown first at normal speed and later by step printing at 1/12 normal speed. The first effect is for the locally weakened surface of the globe to bulge out under the influence of the internal pressure. This bulge then propagates around the globe in the form of a wave, leading to a rather general oscillation. In addition, the detergent can be seen to spread rapidly on the surface of the globe. That is to say, the surface of the globe moves in its own plane away from the area where the surface tension is weakened toward the other side of the globe where the surface tension is still relatively high. The motion is of course limited because there is only a limited supply of detergent, and because the surface on the other side of the globe eventually becomes weakened also. This surface effect is most clearly seen in the sequence with the cloudy globe, where a very small drop of detergent on the upper right-hand side of the globe can be seen to break in, and then the surface to spread quite drastically. So far, we have used the equal density tank to demonstrate the behavior of liquid-gas interfaces in a rather general manner, but in a near zero-G condition. In the next set of pictures, the low-gravity simulation still applies, but the water globes simulate liquid metals discharged from and manipulated by various nozzles, all of which have been so treated as to be non-wetting on the outside. It can be seen that the first globe is somewhat elongated by the inertia of the rather rapid liquid discharge from the nozzle. The inner surface of the nozzle is wetted by the liquid and is quite apparently able to hold the globe or tow it around. A quick pull on the nozzle, of course, can tear it loose from the globe, which for this configuration also means tearing loose a piece of the liquid globe, the smaller globe then adhering to the nozzle. A larger nozzle has much more drastic effects on the simulated metal globe than did the smaller one. Also, the general oscillatory behavior of low viscosity fluids in zero gravity is quite apparent here. Again, a sharp pull on the nozzle can disconnect it, and with it, a proportionately large fraction of liquid from the basic globe. A completely non-wetting nozzle can push the globe around but cannot pull it. This does not exactly simulate the true liquid-gas situation in zero gravity, because always there will be some force of adhesion between the liquid and a solid, such as the nozzle. For our next subject, the situation turns inside out. We now ask you to imagine that the water globe is, or represents, a bubble of gas in liquid metal. The perforated screen has been so treated that the naphtha-freon mixture, that is the simulated metal, wets it, and therefore the water, simulating the gas, does not. This screen can then trap the simulated gas bubble against the wall. The gas bubble does not go through the perforations of the screen because to do so, the radius would have to be very small compared with the characteristic radii of the bubble. To push the bubble through the screen requires a relatively high pressure, and this can only be generated by flattening the big bubble until its characteristic radii are of the same order as the radii of the holes in the screen. It will be noticed that the bubbles, after they penetrate the holes, oscillate very much as did the larger bubbles, but damp out rather more quickly. In addition, they break into each other. They do not coalesce as readily as do gas bubbles in a pure liquid. There seems to be present here some weak relative of the skin effect, which characterizes soapy water, beer, and other liquids which form stable foams or double interface membranes. The membranes shown here are so stabilized. They are relatively insensitive to gravity because they are quite thin and at rather small scale, the whole picture being 2 to 4 inches across. Flat films can be formed on a frame. Hollow spheres can be blown, and flat films can be trapped off of such spheres by a frame, as is shown. This frame, incidentally, did not have to be round. The effect of pressure, or lack of it, in controlling the contour of the film can be seen by the film bulging out in the frame until the bubble on the left, which creates the pressure, is broken. The film then becomes flat. Flat films can also be formed at the intersection of two bubbles. That is, if these two bubbles or hollow spheres are of the same diameter and therefore at the same pressure, the intersecting plane is flat. Two such double interface bubbles can also bounce off each other, break each other, or join to form one large one. The distinction as to just which happens when and why requires a bit of deeper study. In the multiple bubble pictures, the salient points are the flat interfaces and the somewhat involved fact that four of these interfaces join at a point. The creation of foams can be started or initiated by the release of pressure on a liquid containing a dissolved gas, in this case carbon dioxide and water. The pictures in this sequence are about 2 inches wide, and the basic frame rate is about 1/16th actual speed, with the instant replays at 1/100th of reality. The first set shows a considerable amount of gas being released by a rather large, sudden decrease in pressure. The dense foam scene is produced in about 1/4 of a second. The growing bubbles are rising. They coalesce, rise faster, and so on, soon leaving the bottom of the container relatively clear. In zero gravity, of course, the bubbles would not rise, eliminating one of the prime causes of coalescence. A somewhat clearer picture of the birth of the bubbles appears in the next sequence, where a pair of wires twisted tightly together was introduced to provide nucleation points from which the bubbles could grow. A few bubbles may be seen rising to the right of the wire, but most all of the bubbles come from the nucleation points from which they break off and float to the surface. In the third sequence, lucite chips and filings were added to the liquid to serve as nucleation points distributed through the bulk. Only the larger chips are visible in the picture. A very fine foam was produced. As you can see, the bubbles just came out all over the place. It appears that the production of such a fine foam is aided by the presence of the nucleation sources, but it may also be possible to produce it by having a sudden, very large decrease in pressure with only a small amount of dissolved gas present. Bubbles in pure liquids such as water or molten metal will coalesce quickly when pushed together, as by the crowding which appears incipient here. In zero gravity, buoyant crowding will be absent, and control of the total foam volume can define the extent of the direct geometric crowding. Additives to inhibit the coalescence, however, may be necessary and would certainly help to stabilize the foam. For the closing sequence, we return to the equal density tank, in which a half-inch ball of magnesium 141 is neutrally buoyant in a mixture mostly Freon 113 plus a little naphtha. 300-turn solenoids are positioned on each side of the tank and connected to a power supply so that about 1 ampere at 6 kilohertz can be fed to either or both of the coils. With both coils activated and phased so that their fields oppose each other, the ball is impelled from any direction toward the central point halfway between and on the axis of the two coils. Here the magnetic flux should be zero. Eddy currents in the ball react with the driving flux so as to always move the ball toward the weaker field. Damping of the resultant oscillation can be provided by reducing the current in the coils when the ball is moving toward the center. Activate the left coil and the ball moves to the right because the flux is tapered and becomes weaker as it gets further away from the coil. Activate the right coil, the ball moves to the left. But in zero gravity, such as we effectively have here in the equal density tank, the centering condition would be the most useful. This position control and the liquid behavior demonstrations illustrate phenomena which must be considered over and over again in planning space manufacturing.